Okay, guys, this is an example of a procedure on how to determine the lateral forces due to earthquake using the NSCP 2015 lateral force procedure. So we are given here a floor plan, structural floor plan, and a frame uh, considering both the longitudinal and the transverse section. Okay, so what we would like to take a look on here is the regularity of the plan and also the regularity of the elevation or the sections. And they seem to be fairly regular. If we take a look at the plan, the columns here are distributed symmetrically over distances which are normally regular. No? So we have here on the transverse direction a distance of 7.5 each per bay and 6 meters here on the longitudinal direction, which gives us a simple 36 by 15 meter rectangular plan with regular dimensions as far as the column locations are concerned. And if we would interpret that regularity, we can therefore say that the center of rigidity is simply at the middle column. No? So you will, if you are going to take a look at the point of concentration of the columns, we can say that the center of rigidity is actually at grid along grid 4 and grid B here of the plan, and the center of mass is also fairly located at the same point, but of course we have to take note that accidental eccentricity on the center of mass must be considered. So this is now 5% of your dimension horizontal based on the direction. Now, so if we are looking at the movement of your frame in this direction, we will be considering your age as 36. Okay, if we are considering the movement in this direction, we have to consider age is equal to 15. Okay, so take a look at how the value of age is actually determined. No, it has to be based on what direction of earthquake you are considering. Okay, so if this is the consideration, then you use the distance perpendicular to the direction involved. Okay, so in our computation, you will have to take note that age here has two values depending on the direction of your lateral force. If we are going to take a look at the longitudinal elevation or section and also the transverse section, it is also fairly regular. No? So the heights are equal. In terms of the story heights, it is 4.0. Okay, but of course the heights here has nothing to do with the computation of the center of mass and center of rigidity, since um, your elevation or section has no irregularity in terms of verticality. So I will be explaining to you some of the regularity and irregularity issues later when we encounter them in our discussion. Okay, for the given values, we need to have these values in order for us to proceed with the computation. No? So we have here the weights at each story. So these are now the weight, which is computed initially uh, by considering the dead loads, no? So these are due to the dead loads. Okay, for the heights, since this is simply 444, so we have the H1, H2, H3 computed fairly by simply adding the story height uh, over the other. Okay, so your H1, H2, and H3 simply refers to this, no? H1 and then H2 is this one. And H3 is simply this one. Okay, so you are referring to the story height in terms of level 1, 2, and 3. Okay, for the modulus of elasticity of concrete, this is in megapascal. Okay, and of course the occupancy must be determined by the engineer. So here in the problem, it is actually standard occupancy where I is equivalent to 1.0. And the columns are fixed to have a dimension of 0.60 by 0.60 meters. The soil type is SC. Okay, so the location is in Manila so that we can measure the distance of the building from the seismic source. Again, seismic sources are more or less the A, because major fault lines are assumed to be very active, which produces high seismic activity. Okay, our zone is in Manila, so it's zone 4. And the nearness factors NV and NA are directly computed on the basis of the table I showed you in my first video lecture. Okay, so the total weight is simply the sum of all this here. So I just added the W1, W2, and W3. I get my total weight. I think I'm using here units in kilonewton. So these are in meters. Okay, so this is in kilonewton. Okay, for the computation of CV and CA, so these are the formula you can get from the NSCP also. It's 0.56 NV. So I get 0.56 on the basis of these given values. And CA is also 0.4 NA. So I obtained 0.4 on the basis of these two values. So later on, I will show you a program on how to deal with CV and CA automatically using MathCAD. If you want to have an idea on how to determine these values very fast and very accurate, so I have a very simple program to show you later. Okay, R and T are obtained. Of course, R is simply obtained from the table, while T is obtained from the formula CTHN to the 3/4. Okay, CT is fixed as a constant 0.07314 RC frames. Okay, and of course HN is simply the total height, okay, of the uh, structure. So these values here are actually computed automatically by MathCAD. If you know MathCAD, you can simply plug in the given values and then these are automatically computed. So let's go now to the solution of the problem wherein we simply use the formula based on what the code gives us. And the basic formula for base shear is simply this one here. No? So this is actually our main working equation when it comes to base shear. And I just actually separated this factor here for uh, the purpose of looking into the percentage upon which the base shear is compared to the total weight of the dead weight of the building. Okay, so I obtained a 0.14 factor here, which means to say that more or less my base shear is 14% of the total dead weight of the building. And the basic rule of thumb is to consider a range between more or less 0.10 to 0.20. When it comes to buildings, the computed base shear must range from that percentages, 10 to 20%. Although 20% is a little bit very high, but this 14% is actually a very good estimate of how the building will behave in terms of percentages when it comes to lateral forces. No, um, uh, in simple terms, we can say that the lateral force that will be placed on the building in terms of earthquake is simply 14% of its weight. Okay, so that's what this uh, 0.14 factor gives you some indications about uh, the lateral base shear force. Okay, but again, the code needs to check for limitations. No, so we are limited to this value, okay, in terms of the maximum value. So we need not exceed this limit, okay, according to the code. So this is computed on the basis of 2.5 CAI over R W, which gives us a value of 2.65, and this is 3.149. Okay, so which means to say that we cannot use 3.149 because this is greater than 2.65. Okay, so I'll explain this to you more later. Okay, so let's check also the limiting value in terms of the lower limit, which is 991 and 848. No, so we have here two formula on the basis of considering a zone 4. Okay, a zone 4 limitation and an overall limitation. Kaya dalawa ito, no? If you have to check your limitations, the lower limit for base shear, you have to check it for two formula. Okay, so you just check it. I don't know if just the same lecture I have here. Okay, so let's have. Okay, so I think this is the one. Okay, so these are the two formula. Need not exceed. So this is the upper limit, as I've told you, and the lower limit must be checked for all zones. This is the lower, and for zone 4, this is also the lower limit. Okay, so we have two lower limit formula to consider while we have one upper limit formula to consider. Okay. Okay, so if we take a look now on these two formula, we don't have any problem because this is less than what we have computed uh, based on the equation. Okay, now in order to conclude what base shear to use, we cannot overestimate the base shear that the building can handle. Hence, we need to use only this base shear formula, which is again the upper limit based on the NSCP code. So this is the base shear that the building configuration can handle. Okay, so this is now 2650 kilonewton. So I'll explain to you more on this on our discussion on reliability and redundancy when it comes to building configurations. Okay, so for the vertical distribution of forces, Ft is computed on the basis of the formula 0.07 TV if t is greater than 0.7 seconds. But if we are going to take a look at the period that we have computed here, t is not greater than 0.7 seconds. So t is 0.471, and this is simply less than 0.7, which means to say that your structure more or less is not behaving more of um, a low frequency structure, but rather it is of a high frequency structure. Okay, so when you say high frequency, your F is actually um, greater than more or less 1.0. Okay, and if it is less than 1.0, this is a low frequency uh, building. This is a high frequency building. So this 0.7 seconds is actually lower than 1.0, but still this is the basis for determining when to consider the whipping effect. Okay, so the slashing force. So if the frequency of the building is low, then um, sorry, baligtad. If the frequency of the building is high, then your period is low and therefore slashing effect is not considered. So this is now Ft is more or less equivalent to 0 here. So that's why if we're going to take a look at this uh, uh, Ft computation here, when t is less than 0.7 seconds, okay, we only obtain a 0.471 t here. So we fall on the Ft is equal to 0 value. So we can disregard Ft here on the formula and just consider the V here, the base shear solely, and compute for the forces on the basis of this equation. Okay, so this is a MathCAD tool. If you want to do it in a tabulated manner, you can just uh, tabulate it. Let's say this is the story. Okay, and then you have the W, you have the H, okay, and then you have the WX, HX. Okay, so you just tabulate like this and fill up the spaces here, the blanks. You get the weight here, and then the HX here, and then multiply the weight and the height, okay, such that you will get these values here. This is now the summation WX, HX, which is basically this one on the denominator, okay. So this is the denominator upon which your factor here, okay, your factor will then be computed. So this is actually a coefficient or a factor. Okay, so you just divide this first value with this summation, and then this second value with this summation, and this third value with this summation, and you get these factors here, upon which If I multiply each factors with V, I will get now the story forces F1, F2, and F3. Okay, note that these forces are for the whole building. So we still need to distribute these forces horizontally later as shear frame forces. So I will be explaining to you this in detail on the next video. So for now, I'd like you to understand how the main working equation for base shear is used, including the limitations and how it is distributed vertically over the height of the building. So thank you very much for listening. I'll see you in the next video.